Hi, I'm Ryan Vandermark.
Hi, my name is Monty Susanna.
Hi, my name is Sienna Samuel.
Hi, I'm Isabel Olivas, and we're Team 22088, and our senior design project is optimization of Cave Creek wastewater treatment. Why do we care about wastewater treatment anyways? It's a preventative measure against forms of diseases and contaminants and toxins. It helps protect humans and the ecosystem. And in Arizona particularly, it's a valuable resource that we can reclaim. Alright, so this is a little bit about Cave Creek. So it's a town right outside of Phoenix on the northeast side. It serves a community mainly comprised of primarily seniors, and right now they have a wastewater plant that has a capacity of 8 million gallons per day. So this is our problem statement. We're evaluating the population projections and historic water characteristics data to develop a recommendation for design flow capacity, researching potential discharge options for the effluent, determining improvements that can be made to meet desired future treatment capacity and water quality parameters. And then we also have some emphasis placed on optimizing the process for overall treatment effectiveness.
Here are our calculations for population projection, and these are for the influent.
We made two decision matrices as per the problem statement. The first one was for the effluent uses. So we considered recreational impoundments, golf course irrigation, toilet to tap, livestock watering, food crop irrigation, and discharge to surface. Discharging the treated water was ultimately chosen as our final effluent use, and this is because it's the most cost-effective option, it's appropriate for the current plant layout, and it's also appropriate for the mass balance, and it was also appropriate for the surrounding community and environment. And then the second decision matrix that we did was for our treatment process. So we considered adding a grit chamber, an equalization basin, an anaerobic reactor, reverse osmosis system, struvite collection system, and emergency overflow basin. Ultimately, we chose to add an aerated grit chamber and an anaerobic reactor. The grit chamber will remove the grit to help prevent damage to downstream equipment, and the anaerobic reactor will help us meet our water cleanliness standards and allow for struvite or biogas collection in the future. And both were feasible additions to the plant overall in terms of cost and physical space.
This is the process flow diagram for the Cave Creek wastewater treatment plant. First, the influent comes in through the pump station, and then it goes to the headworks so that large pieces of grit and other materials are removed before they damage the rest of the equipment. Then, at stream 6, there is a three-way split. Some of the waste ends up in the storage drum because it is not treatable, some of it goes through odor control, and the rest goes to the primary clarifier, the anaerobic digester, and an aerobic reactor. After that, it splits into two different streams where it goes into two different secondary clarifiers. One of the secondary clarifiers goes into a recycle stream to settle as much of the solids as possible. The other secondary clarifier takes the water to the tertiary filter, UV disinfection, the effluent pump station, and finally the reclaimed water storage basin.
So this is Biowin, a modeling system specifically for wastewater treatment. We were able to model Cave Creek's wastewater treatment plant here. We weren't able to model every piece of equipment, such as the headworks, the odor control, tertiary screens, UV disinfection, and the reclaimed water basin, but we were able to model everything in between. So our model starts here with our influent coming from the headworks. It's sent to our aerated grit chamber, and then the primary clarifier, and then it's sent to our reactors. This reactor system is called a faux redox process, which just means an anaerobic digester followed by an aeration basin and then eventually a recycle stream. So the reacted water is sent to our secondary clarifiers. The processed water comes out here and is sent to the tertiary screens and further treatment, and then our sludge is settled out, with most of it being recycled back to the reactors, and a small portion of it being sent to waste. The tags on all the equipment and the piping are very helpful with modeling, and then Biowin has a very helpful feature called the album feature, and here it gives us a full stream table.
So first, the influent comes into the plant and then is pumped from the influent pump station to the headworks. The headworks is the first stage of the treatment process, where large debris is removed at the bar screens and grit is removed in an aerated grit chamber. Everything that's filtered out from the bar screens in the aerated grit chamber is ultimately sent to a landfill after it is collected.
And then the sludge. And then the purpose for the tertiary filters is to enhance the quality of the discharged effluent to minimize impact on the surrounding environment. And the expected concentration is around 10 ppm of BOD and 10 ppm of suspended solids. And it's really important for secondary reuse due to drought in many areas globally. And the filter media system used is the dual media with anthracite and black sand. And for the tertiary filter to work properly, it is important to add polyelectrolytes to encourage coagulation. So now I'll be talking about anaerobic and aerobic reactors. So the anaerobic reactor, as Sienna was saying, can be used for biogas production. And during anaerobic digestion, organic waste is biologically degraded and converted into gas. Temperature is kept at 35 degrees Celsius, and usually a heat exchanger is added onto the digester. And then there's the aerobic reactor, which is also known as the aeration basin, and it involves close contact of the water and the air for removal of dissolved gases and oxidation of dissolved metals such as volatile organic compounds and hydrogen sulfide. And it basically occurs by exposing the water to thin sheets of air and then letting the air rise through water. So for odor control and disinfection, these are very important parts of the process because they reduce impact on the surrounding environment and ensure public satisfaction. So the primary and chemical odor control system involves coverings at the aerated influent channel, coverings at the sedimentation basin effluent wares, coverings at the sedimentation basin, and then effluent channels, and finally conveyance ductwork from capture locations to the odor control system. And in this process, bioscrubbing technology is also an important aspect because it removes hydrogen sulfide, which is one of the main causes of odor problems at wastewater treatment plants. And then for UV disinfection, this is a process that tends to be more effective than chlorine disinfection, and the wastewater is basically treated with UV light to destroy the bacteria and the virus's structure, which leads to prevention of infections. And this is an extremely effective method as it can limit the functions of the organisms in a matter of seconds.
So some of the optimization recommendations that we would recommend for the plant now and the future, the first is the grit chamber and the second is the anaerobic reactor. These are two pieces of equipment we would recommend that the plant implement now. The first to remove some of the grit that will harm downstream equipment, and then the second will help us meet water cleanliness standards and will also help us open up the possibility for a biogas and struvite collection system in the future. We would also recommend that the plant look into direct potable reuse of water. This is also called toilet to tap, and this will help combat the emerging issues of water scarcity in the future. And then we would also recommend that the plant look into plant expansion as population grows. This might mean adding new equipment or just assessing what needs to be done to accommodate increasing influent. And then finally, we would also recommend adding different equipment for struvite and biogas collection. These would be good revenue streams for the plant, and then they would also be good for repurposing some of the waste that the plant produces.